The final example I'd like to go over in our study of centripetal force is for the case of what we call a banked curve. So we see a lot of these on freeway on-ramps. If you would like to decrease the radius of curvature so you don't have to use as much asphalt in paving a highway, then instead of just relying on friction to provide centripetal force, you can rely on friction and a component of normal force, provided that the roadway is banked at some angle. So what are the forces acting on this pickup truck as it drives on this segment of road? Well, there's definitely a normal force pointing this way. And we can't ignore the downward pull of gravity. Now, is there friction? Yeah, most likely. By the way, the friction in this case, even though the car is in motion, is not kinetic friction, it's static friction. And I think in a previous lesson, I reviewed this concept of rolling friction and the way in which a tire, when it rolls in this direction, at one moment in time has a contact point with the road. If you're skidding, there's relative motion between the contact point and the road. But if you have a pure rolling type motion, then that contact point has a relative velocity with the road of 0. And so this is actually static friction, not kinetic, right? If the tire rolls onto this place, the point that was the point of contact has moved here, a new point of contact is established, but still the velocity between that point and the road is 0, unless you're skidding. So, yeah, there's a coefficient of static friction available. Now, maybe the car drives on an oil slick or an ice patch. I think the car could still navigate the banked curve if it travels at one perfect speed. So we'll solve that problem first, and then we'll get into the case where, what if there's not this oil slick? Then which direction does the frictional force point? Well, it depends on whether the car drives fast or slow. It could be the case that the force of friction points this way, parallel and up the incline, or it's possible that the frictional force points this way, parallel to and down the incline. So I'll let you think about that for a moment, but first we'll solve the more simplified case in which there's no friction, such as encountering an ice patch on the road. Now, one thing we need to keep in mind is what's the direction of the acceleration for this vehicle. So as this car drives around the banked curve, it's not going to increase or decrease its elevation, right? It's going to remain in a circular path on a horizontal plane, so the centripetal acceleration points along our x-axis. So that informs us of how we want to resolve this free body diagram. Now, in previous studies in this unit, where we've seen objects on inclines, we made the x-axis run parallel to the incline and the y-axis go perpendicular to it. So when we saw a free body diagram where normal force pointed at an angle and gravity pulled straight down, we broke gravity into components that lie along the y and the x-axis. But this case is different. We don't want to make, well, the reason we made the x-axis parallel to the incline and the y-axis perpendicular is we always want the x-axis to be the axis of motion or the axis of acceleration. And when you release a block of ice, for example, at the top of a ramp, it certainly accelerates parallel to the incline. But you can see here, what I'm suggesting is this pickup truck does not accelerate parallel to the axis. There's no increase or decrease in the vehicle's elevation. Its acceleration is entirely along the x-axis. So we don't want to break mg into components. This is a case where we want to break the normal force into components. If we draw this force diagram free of the object, then we should choose an x-axis that points in this direction. So the y-axis points this way. Yeah, so mg is not broken into components. Now, we need to figure out if we label this as theta, the angle of the banked curve, then where does that theta show up in this force diagram? Would it be that angle? Or would it be this angle? Well, how about you imagine only very subtly banked curve? Then what's that going to do to this normal force? Wouldn't it take it and make it point more vertically? So in other words, as this angle theta gets smaller, this angle theta is also getting smaller, right? Yeah, so hopefully that answers the question. And you realize that if we label the angle of the incline as theta, then the angle between the normal force and the y-axis is that same angle theta. Okay, so let's proceed here and answer the question based on the case where there's no friction. So we suggest something like an ice patch on the road. So let's just do this one more time. Draw the free body diagram. So free of the object, let's show the forces. Normal force points this way, mg points this way, and don't make the mistake of making your x-axis parallel to the incline. That is not the axis of acceleration. We're going to make the x-axis the axis of acceleration. So x is horizontal, y is vertical, and this angle theta is the same as this angle. So now we make it a resolved free body diagram. So there's a component to the normal force pointing up. That would be n cosine theta or n sine theta? Cosine, right? Sure. The component of a force that lies adjacent to the labeled angle is always found using cosine, and the component that lies opposite this labeled angle is the one associated with sine. So there's a component to the normal force n sine theta pointing to the left. There's a component of normal force pointing up, and there's the force of mg. So this upward component to the normal force cancels out the weight of the vehicle, which is why there's no motion up or down the incline, right? There's no acceleration along the y-axis. The acceleration that's centripetal is entirely in the x-axis. And in fact, there's nothing to balance out this force, and it shouldn't be balanced. This is not a case of equilibrium. When things move in circles, there's definitely a net amount of force. There's an overall acceleration. And we can see then in this case, n cosine theta is equal to mg, and then you're left with n sine theta as the unbalanced amount of force. In other words, it's the net force. In other words, it's ma. This is centripetal acceleration, so in other words, it's mv squared over r. Now this should look very familiar at this point. We get equations that look very much like the work we had in our investigation of the conical pendulum. The only difference was that we had components of tension as opposed to components of normal force, but the equation's nearly the same, and our approach is going to be the same. We're going to divide one equation by the other. That cancels out normal force. Mass also cancels out, and we find that tangent theta is equal to v squared divided by rg. So we can say, what's the one singular safe speed if we know the angle at which the roadway is banked? So let's say the road is banked at an angle of 20 degrees, and there's a radius of curvature of 75 meters. Then what's the, well, it's not so much a minimum or a maximum safe speed. If the car goes too fast, it's going to slide this way off the road. If the car goes too slow, it's going to slide this way down the road. So there's one sort of Goldilocks speed that the car would have in order to navigate around the curve if the roadway is all covered with ice. So what is that speed? It's equal to the square root of rg tangent theta. So given the numerical values we have in this case, v is equal to the square root of 75 times 9.8 times the tangent of 20 degrees. Let's grab a calculator and see what we get. Well, we get a value of 16.4 meters per second, which is about 35 miles per hour. And on roadways like this, you may very well see some sort of posted safe speed sign, right? And notice that the speed sign doesn't come in a series, right? It doesn't like have one speed sign for sports cars and another one for trucks and so on. My point being that mass canceled out of the equation. So whatever is the safe speed for a light vehicle is the same safe speed for a heavy vehicle. Now this problem becomes significantly more challenging if there is friction, and you'll see what I mean here in just a moment. So let's consider the case where the vehicle is driving too fast for the given angle and coefficient of friction. So let's just think about it. If the car goes if it goes too slow, like it's parked, let's say, and this angle is really steep, the tendency would be for the vehicle to start to slide down the incline, right? Provided there's not enough coefficient of friction for that given banking angle. At low speeds and zero velocity, if anything, the truck certainly isn't going to start to slide this way up an incline while it's parked. That would blow your mind if you saw something like that. I don't think you would be surprised to see a parked car start to slide this way if the angle is fairly steep. So at low speeds, to prevent that from happening, the friction force would have to point up the incline to keep it from sliding. However, this is the case of driving too fast. And if you drive too fast, the car won't be able to follow the curve. Instead, it follows the law of inertia and tends to fly this way, which means ultimately its motion would bring it farther away from the center of the circle and up the incline. And so the frictional force would have to point back this way to prevent it from doing that. Okay, so see what I mean? Conceptually, this problem's challenging, and we'll also see just with the trigonometry and the algebra involved, there's a bit more substitution work to be done. But at the very least, now we know how to make our unresolved free body diagram. Normal force points in this direction, gravity points in this direction, and when the car drives too fast, the friction force points in this direction. So what are our x and y axes? Here and here. You may have a desire to break mg into components by making coordinate axes that point this way, but that would be a big mistake because the x-axis should be the axis of acceleration, and I guarantee you the vehicle is not accelerating on this axis. As long as there's enough friction provided, the vehicle will be accelerating in a horizontal plane. So we're going to get rid of this free body diagram. That's the wrong approach. This is the correct way to go. So we're not going to break mg into components, but for our resolved free body diagram, we do have to break normal force into components, and we have to break the friction force into components. Now I've labeled the angle of the incline in my free body diagram. Hopefully you agree that I've labeled correctly. So we don't have to do anything to the force vector mg. It continues to point straight down. There's a component to the normal force that points upward. We'll draw that again. Now notice, it looks like I've drawn that longer than mg. Well, for good reason, because there's a component to the friction force that would point downward, right? And hopefully the upward normal force cancel these two downward force. So this downward force is a component of friction. That would be F sine theta. And then there are two components pointing toward the center of the circle. There's the component of friction, F cosine theta, and a component of normal force, n sine theta. Okay, so how do we show that there's equilibrium along the y-axis, but there's not equilibrium along the x-axis? Well, we can state that the normal force has to be equal to f sine theta plus mg. So that covers the idea that there's equilibrium along the y-axis. The upward force and the two downward forces tend to cancel each other out. And then how do we show that there's an overall net force along the x-axis? Well, we say that the net force is provided by the combination of f cosine theta plus n sine theta. Oh, and my bad. I mean n cosine theta here. I left off the key information, didn't I? Shame on me. Make sure we fix this. You probably already caught that. This is n cosine theta, right? So the upward force balances the downward forces, and the upward force is just a component of the normal force. Now, what are we going to substitute for net force? Yeah, of course, ma. And it's centripetal acceleration. So I guess we really mean mv squared over r. Don't want to get ahead of myself. So a preview of coming attractions here. We're going to do the same work in the case of driving too slow next, but we're not there yet. Okay, forgive me. Oh, back to the task at hand. So, how do we rearrange this equation? Let's see. I'm going to rewrite the top equation. So notice this first top equation has to do with our forces on the y-axis, and the second equation has to do with forces along the x-axis. So let's rewrite this. We'll say mg is equal to, how about n cosine theta minus f sine theta. Okay, that's good. And how about we rewrite this one just a little bit? We'll just clean it up. mv squared over r is equal to n sine theta plus f cosine theta. Well, let's do as we did in the previous problem and divide one equation by the other. M cancels out. We get v squared over rg is equal to n sine theta plus f. Let's see, what's f? Well, f is equal to mu times normal force, right? So mu n cosine theta divided by n cosine theta minus mu n sine theta. Well, now there's an n in every single term, so we can cancel all that out. And then I suppose we can divide numerator and denominator by cosine theta. What would that give us? So every term in the numerator is getting divided by cosine theta. So this becomes sine over cosine, which give us tangent theta. And of course, if we divide mu cosine theta by cosine theta, we just get mu. So we have to do the same thing in the denominator, divide everything by cosine theta. Well, cosine theta divided by cosine theta gives us 1. And then sine theta divided by cosine theta gives us tangent. So that's a pretty nice way to write it. So now we get, if we just multiply both sides of the equation by rg, and then take the square root of both sides, we have v equals the square root of rg times the quantity mu plus tangent theta, all divided by 1 minus mu tangent theta. Interesting. Interesting because I want to see if we can apply this equation to the case that we solved earlier of driving on the bank curve with an ice patch. In other words, when mu is equal to 0. Now, what was our result for this equation? Our result was v equals the square root of rg tangent theta. Well, let's just see what we get from this new derived equation in the case where we plug in u equals 0. Then we get v is the square root of rg times 0 plus tangent theta divided by 1 minus 0. Yeah, we get v is the square root of rg tangent theta. Oh, so this equation works for the case of friction as well as the case of no friction if you're just willing to plug in 0 for mu. And the other interesting thing is we can apply this to the case of a flat road. So we've asked the question before, what happens when a car drives around on a circular track? So there's our vehicle, normal force points up, mg points down, and the friction force points straight inward. And I think we found that the safe speed here is the square root of mu times g times r. Now, let's see if that's what we get in the case of a flat road. Well, flat road just means the angle theta is equal to 0. So what would we get if we plugged in 0 for theta? We would get the square root of rg times mu plus 0 over 1 minus 0. Well, yeah, we get the square root of mu gr. So this seems to be an equation that covers all possible cases: flat roads, banked curves with no friction, and also banked curves with friction. However, there's one more case in which this equation wouldn't work, and that's in the case of driving too slowly. Now, if the car goes too slow, our free body diagram changes just a little bit. We still have normal force pointing at an angle. We still have mg pointing down, but when the car drives too slowly, the direction of the frictional force changes. Instead of friction pointing in this direction to keep the car from having motion up the incline, the friction force at low speeds would have to point up the incline to keep the car from sliding down to the bottom of the incline. So again, we're going to make an x-axis that's horizontal and a y-axis that's vertical, and so the angle theta appears in these two positions on our free body diagram. We need to change this into a resolved free body diagram. I'll try not to make the same mistake I made in the previous case. This isn't just n, this is n cosine theta, and in that same direction is a component of the friction, f sine theta. Then we leave mg by itself pointing down, and now we have a component of force this way, that's n sine theta, and we have a component of friction this way. Now, notice I've drawn the component of friction to the right smaller than the component of normal force to the left. Now, that might not exactly agree with the way I drew the forces here. Maybe I should have drawn a shorter friction force. Okay, now that looks better. I know that the force to the left has to be greater than the force to the right because, after all, the vehicle's acceleration will be to the left. Okay, so what do we have here pointing to the right? This is f cosine theta. So let's take a look at the y-axis first. Along the y-axis, we can say mg is equal to n cosine theta plus f sine theta. We look at the x-axis, and we notice that the net amount of force, which is mv squared over r, is going to be equal to the difference between the force to the left, n sine theta, minus the force to the right, f cosine theta. If I rearrange, then I can divide one equation by the other. I guess I could divide whether I rearrange or not, but I prefer to divide in this order. So mass cancels out, and we get v squared over rg, and then on the right we have a numerator n sine theta minus f cosine theta divided by n cosine theta plus f sine theta. But we can substitute For f, we can replace it with mu n. And now there's an n in every term. This should look familiar. So we have v squared over rg is equal to, and let's do the same trick we did before. We're going to divide the numerator by cosine theta, and we're going to divide the denominator by cosine theta. So we get tangent theta minus mu divided by 1 plus mu tangent theta. So v is the square root of rg times tangent theta minus mu divided by 1 plus mu tangent theta. Now how does that compare to the equation we had when the vehicle drives too fast? Well, let's see. Let's just copy this and paste it below and see how the two compare. Oh, well, the difference is in the numerator, positive and negative have changed, and in the denominator, negative and positive have changed. Okay, so if you try to commit these equations to memory, it's going to be way too easy to make a mistake. So in the end, if you have problems like this, it's very much worth your time to rederive the equation based on the resolved free body diagrams. Now that takes some time and some thought, but that's the whole point of this study of physics, is to conceptualize the problem and work your way through the derivations as opposed to memorizing the final results. So that represents a fairly challenging problem. I'll leave it up to you to try to find some numerical examples where you have to apply these equations in your homework. The numbers are always the easiest part. It's the derivation that takes some time. So if you want to replay, rewatch, or rederive any of the equations you found in this video lesson, feel free to pause, rewind, or watch again. And as always, thanks for watching.